Imagine walking into a city and seeing a skyscraper standing perfectly upright, but with no steel frame, no internal skeleton, no load-bearing structure, just walls, windows, and air. According to everything we know about engineering, that building should collapse immediately. Not after decades, not after centuries, instantly. Now scale that idea up to a galaxy. In 2018, astronomers reported the cosmic equivalent of that impossible skyscraper. A galaxy that appeared to exist with almost no dark matter. Its name is NGC 1052-DF2, and depending on who you ask, it is either one of the strongest pieces of evidence that dark matter is a real, physical substance, or a warning about how fragile our measurements of the universe really are. Because if a galaxy can survive without dark matter, then something fundamental has to give. Either dark matter can be removed from a galaxy, or our understanding of gravity itself is incomplete. In modern cosmology, galaxies are not supposed to form from normal matter alone. In the standard lambda CDM model, dark matter is not optional, it is structural. In the early universe, dark matter collapses first. It forms gravitational wells long before stars exist. Normal matter falls into those wells, cools, and eventually ignites star formation. Galaxies grow inside invisible halos that dominate their mass. Remove dark matter from this picture, and the model predicts something simple and very uncomfortable. Galaxies should not form at all. That is why, in the Milky Way, dark matter outweighs normal matter by roughly 5 to 1. The stars we see, the gas we detect, the dust we map, all of that is just the visible frosting on a much larger invisible cake. Dark matter is the framework holding everything together. Without it, spiral galaxies should not remain stable over billions of years. We do not see dark matter directly. We infer it from motion. Since the 1970s, especially after the work of Vera Rubin, astronomers have known that stars and galaxies orbit too fast to be held together by visible matter alone. If you calculate the gravitational pull produced by stars and gas, it is not enough. At those orbital speeds, stars should gradually drift away into intergalactic space. But they don't. Something unseen provides additional gravitational pull. That unseen component is what we call dark matter. Unless, of course, gravity itself behaves differently at extremely low accelerations. That alternative idea is known as modified Newtonian dynamics, or MOND. Instead of adding invisible matter, MOND proposes that the laws of gravity subtly change in regimes where accelerations become extremely small. MOND can reproduce many galaxy rotation curves remarkably well, but it struggles with other observations, especially on larger cosmic scales. And this tension between dark matter and modified gravity is exactly why DF2 became such a battleground. NGC 1052-DF2 was not discovered with a traditional giant mirror telescope. It was found using the Dragonfly telephoto array, an unusual instrument made from commercial camera lenses working together. Dragonfly is optimized to detect extremely faint, diffuse light, the kind emitted by ultra-diffuse galaxies. These galaxies are large in size, but contain very few stars, making them almost transparent against the background sky. Most telescopes are not designed to see them well. Dragonfly is. DF2 is one of these ultra-diffuse systems. It is spread over a region comparable in size to the Milky Way, but it contains only about 1% of the stars. You could almost see distant galaxies through it. Visually, it already looked strange, but appearance was not the shocking part. Mass was. You cannot put a galaxy on a scale, so astronomers estimate mass by measuring motion. In DF2, the tracers used were globular clusters, dense, compact groups of stars orbiting the galaxy. These clusters act like test particles moving through the galaxy's gravitational field. The stronger the gravity, the faster and more chaotically they should move. In a galaxy with a normal dark matter halo, the globular clusters should exhibit a relatively high velocity dispersion, a wide spread of speeds reflecting strong gravitational binding. Instead, the measured dispersion in DF2 was extremely low, only a few kilometers per second. Even at the upper end of the estimates, around 10 kilometers per second, roughly 22,000 miles per hour, The speeds were remarkably slow by galactic standards. That matters because velocity dispersion directly translates into mass. And when astronomers converted those speeds into a total gravitational mass, they found something startling. The mass inferred from motion was barely higher than the mass expected from the stars alone. There was little room left for dark matter. The invisible framework appeared to be missing. The skyscraper had no frame. When these results were published, the reaction was immediate and intense. Not celebration. Scrutiny. Extraordinary claims do not get a free pass, especially when the data are difficult and the number of measured objects is small. Critics focused on two main vulnerabilities. The first was statistics. With only a limited number of globular clusters, velocity estimates are sensitive to outliers and measurement uncertainties. But the second issue was far more serious: distance. In astronomy, distance is everything. If DF2 is farther away than assumed, then it is larger and more luminous, and its stellar mass increases. If it is closer, the stellar mass drops significantly, and suddenly, dark matter may be required again to explain the observed motions. A relatively small change in distance can completely alter the conclusion. Some researchers argued that DF2 was only about 42 million light-years away, rather than over 70 million as originally estimated. At that closer distance, the anomaly weakens. Dark matter would no longer be absent, just reduced. To resolve this, the original team turned to one of the most reliable distance indicators available: the tip of the red giant branch, measured using the Hubble Space Telescope. Red giant stars reach a well-defined maximum brightness before undergoing a rapid internal transition. That brightness is known from stellar physics. By measuring how faint the brightest red giants appear in DF2, astronomers can calculate its distance with high precision. After dozens of Hubble orbits and careful analysis, the result came back. DF2 was farther away, not closer. Roughly 65 to 75 million light-years, depending on assumptions. At that distance, the original conclusion held. DF2 was severely deficient in dark matter, by factors of hundreds compared to typical galaxies. Then the situation became even more uncomfortable. Astronomers identified a second galaxy in the same group, NGC 1052-DF4, another ultra-diffuse galaxy, another extremely low velocity dispersion, another apparent lack of dark matter. At that point, the debate shifted. The question was no longer whether the measurements existed, but how such galaxies could form at all. Several explanations were proposed. One involves violent interactions early in the galaxy's history. Normal matter interacts. It collides, shocks, cools, and sticks together. Dark matter does not. In a high-energy collision between gas clouds, normal matter can clump and form stars, while dark matter simply passes through, leaving behind a galaxy dominated by stars, but deficient in dark matter. Another explanation involves tidal stripping. DF2 and DF4 are located near a massive elliptical galaxy, NGC 1052. Over billions of years, gravitational tides could gradually peel dark matter away more efficiently than stars, especially if the dark matter halo was extended and loosely bound. None of these explanations are fully settled, but they all share one crucial assumption. Dark matter behaves like a physical substance, something that can move independently of stars, something that can be displaced, stripped, or lost. For decades, physicists have searched for dark matter in underground detectors and particle accelerators. So far, they have found nothing. That absence has fueled skepticism and revived interest in alternative theories of gravity. But DF2 changed the nature of the debate. If gravity alone were responsible for galaxy dynamics, then every galaxy should behave consistently under similar conditions. You should not be able to have one galaxy that appears to need extra gravity and another that does not. But if dark matter is real matter, then rare exceptions make sense. You can have a bucket with water, and you can have an empty bucket. NGC 1052-DF2 may be that empty bucket. This faint, ghostly smudge of light, tens of millions of light-years away, may represent a rare accident of cosmic history. Or it may be pointing towards something deeper, a universe where matter and gravity are not always locked together, where structure can exist without the invisible glue we once thought was mandatory. The galaxy with no dark matter should not exist, and yet it comes uncomfortably close. And that tells us something profound. The most important structure in the universe may be the one we cannot see. And if you want to keep exploring the universe where the rules begin to break, subscribe and stay with us. Veil Origins: Impossible Truths.